All right. So we are going to just kind of review over the concepts we were talking about before break. So let me know if I'm going too fast or you can't read my writing. So 3 basic groups that you need to be familiar with from your periodic table are your metals, your nonmetals, and your metalloids. And then you do need to be familiar with some of the just very general physical and chemical properties of each, because we talked about how we can use physical and chemical properties to identify a mystery element, and we're still discussing that same concept, but even familiarizing ourselves more with this in relation to the different families of elements. So do it back here because that one's better. Your properties of metals, they tend to be good conductors of heat and electricity. So that's a physical property. And what that means is they can move heat and electricity. So, if you have a metal spoon and you put it in a hot pan of soup on the burner and you touch the spoon, it's going to feel hot. And that's because metals can move or conduct heat energy. We also know that we use metals in wiring for electrical appliances because metals will allow the electricity to flow. So metals can also be pulled into wires, and so they're said to be ductile. Another physical property, they can resist a tensile force. So you can pull outward on the metal and it'll stretch and not break into the form of a wire. They can also be flattened and pounded into different shapes and so are said to be malleable. And metals are shiny. These are physical properties of metals. One of the most important chemical properties that you definitely need to memorize is that when you're a metal, you tend to give up electrons when you react with other elements. Okay, that's a big one. That's a chemical property. Remember that elements are always trying to get a full valence or outer ring or 8 electrons in their outer ring, and they'll do anything to get that. So, for example, this we can really, kind of drive home the point by looking at an example. If we look at the first 2 columns of elements, these are our alkaline metals and our alkaline earth metals. Everybody in column 1 has 1 electron in their outer ring, 1 valence shell electron. So if you look at lithium, it's got 1 here. If you look at sodium, it's got 1. Potassium, 1. They all have 1 valence electron. But what I really want you to notice is when the atom gives up its 1 valence electron, because all of the alkali metals love to do that, then the next ring is full. So if sodium, it's got 281. 2 electrons in its first ring, 8 in its second, 1 in its third. So when sodium gives up 1 electron, that ring disappears, and the ring below that has 8 electrons. That's a full valence. Potassium, same way. When it gives up its 1 valence electron, it's got 8 in its outer ring. Same thing is true for column 2. These are the alkaline earth metals. They all have 2 electrons in their outer ring. So if you look at the last number for all of these elements, it's always 2. So being a metal, they like to give up electrons, and specifically the alkaline earth metals all give up 2, because when they give up 2, their new valence ring either has 8 or is full. Make sense? Okay. So again, metals like to give up electrons. So properties of nonmetals are pretty much the opposite of your metals. So they are poor conductors of heat or electricity. So we would never use plastic in the wiring for a lamp because it would not move electrons. It would not conduct electricity. It might be a good thing to use in terms of a spoon because it's not going to be a good conductor of heat energy. And so if you have the spoon resting on the side of the pan, it's not going to burn your hands as readily. So unlike metals, they are not ductile or malleable. Okay, if they are solids, They're not shiny, they tend to be dull. And those that are solid are brittle, and when you put a force on them, they'll crumble and break. They don't bend, or they're not pounded into shapes very easily. Okay? Many of them are gases at room temperature. And then I left off a very important chemical property of nonmetals, and that is they tend to steal or share electrons when bonding and reacting with other elements. Okay, unlike the metals, they don't give up electrons, they steal them or they share them with another atom as they react and make chemical bonds. Okay, so all of the physical properties and chemical properties are pretty much the opposite of what they are with the metals, so be familiar with those. Then finally, the metalloids, they have properties of both the metals and the nonmetals. So they share properties of both. And what those properties are depend on lots of different conditions, including maybe the temperature. So under certain temperatures, maybe the metalloid acts like a metal, and under other temperatures, it acts like a nonmetal. So they are solids at room temperature. Okay. They, like metals, conduct electricity, but not as good as metals. Okay. Because it's only under certain conditions. Sometimes they don't. That's why we call them semiconductors. Okay. Because they will conduct electricity under certain conditions and temperatures and not under others. So just like Hemlock Semiconductor processes silicon, silicon is a semiconductor. It is a metalloid. It will conduct electricity under certain conditions, but not under others. And for whatever reason, that makes it a very valuable product in electronics, like cell phones, computers, and things like that. Okay? Your metalloids tend to be ductile and malleable. So these are some of the physical and chemical properties to get familiar with your metals, nonmetals, and metalloids. Now, next thing I want to do is talk about the individual families and some of their physical and chemical properties that I think will help you be more successful if you're making up an assignment that you had trouble on, redoing it, and even some of the stuff we're going to be doing tomorrow. So elements in the same column, remember your columns run up and down, or in the same family. A column is called a family or a group. And their claim to fame is that they have the same number of valence electrons. Okay? And so all of the elements in the same column react similar to each other. So just as I said before, family 1, all of those elements tend to lose 1 electron. Family 2, they tend to lose 2 electrons. When we get over here, besides boron, the rest of these are metals. They tend to lose 3 electrons. Remember, this family 13 has 3 valence electrons. Families 14, 15, and 16, they all tend to share electrons. So the carbon family has 4 valence. They need 4 more to make 8. That's stable in the outer ring. So they will share 4 electrons. These guys in the nitrogen family all have 5 valence electrons. So how many would they share with another element, you guys, if they have 5? They want 8. Say it out loud. 3. Good. What about oxygen? How many bonds is it going to make, or how many electrons is it going to share if it has 6? 2. Good. 7, 8. Okay. These guys over here are all going to want to steal 1 electron because they have 7. They want 1 more to make it 8. And these guys don't react. So if we're in the same family or group, we tend to react similarly because we have the same number of valence electrons. So their chemical properties are very similar. Now, elements in the same row, like this, or period, have the same number of rings of electrons. Okay, so we labeled this in some of your prior notes, but just to show you, if you're in period 1, which is hydrogen and helium, you have 1 ring of electrons. If you're in period 2, which is lithium all the way through neon, you have 2 rings of electrons. If you're in period 3, which is sodium, all the way through argon, you have 3 rings of electrons, and so on. Okay? So be familiar with what your period and your family numbers mean. All right. So now let's go over the individual families really quickly, just to review is what this should be. So we're going to talk about the first family, which is right here, hydrogen through francium. This is the alkali metal family. Remember that hydrogen is an exception. It's placed in that family because it has 1 valence electron, but it's really not a metal. It's a gas at room temperature. The alkali metal family is the most reactive group of metals. These metals are always found in the form of compounds in nature. Why? Because they're so reactive, they're never going to be found alone. They're always going to react with another element to make a compound. You're never going to find them by themselves. Okay? They tend to be shiny metals. They're also soft. These are some of their physical properties. A chemical property is that they tend to give up 1 electron when reacting with other elements. And we just talked about why. Okay? They are violently reactive with water. So, for example, if we look at something like sodium, okay, its atomic number is 11. If you look on the periodic table, it has 2 electrons in the first ring, 8 in the second, 1 in the third. So you can see that if it were to give up 1 electron, as I've mentioned before, then it has 8 in its outer ring, and that makes it very stable. Okay? So elements are always looking to either have a full valence shell or 8 in that outer valence ring. And that makes them very stable and unreactive. Okay? Plug in here. Okay. So now the second family of elements is our alkaline earth metals, which is family number 2. A lot of you are familiar with them because they contain elements like calcium and magnesium, things that we find in the human body. Okay? It is a very reactive group, but not quite as reactive as the alkali metals. Remember, we talked about before that as we move from left to right, from here to here, just within the metals, just where the transitions end, the reactivities of the metals get less and less and less. With the most reactive here, a little less reactive, just within the metals though, okay? And so when we look at the metals that are on the right side of those transition elements, those are the ones we're most familiar with because they're not so reactive that they're going to explode. So we use them in jewelry and buildings, making airplanes and cars, things like iron and copper, silver and gold. All of those are going to be less reactive than these first couple of columns, okay? So the alkaline earth metals are a little less reactive than the alkali metals. They are also never found alone in nature. They tend to give up 2 electrons because remember, when they give up 2, what's revealed is the next level is going to have 8 or be full, and so it'll be non-reactive. So one of the elements in column 2 we could look at is calcium. Okay, so its atomic number is 20, and it has, according to the periodic table, 2 in the first ring electrons, 8 in the second ring, 8 in the third ring, and 2 in the fourth ring. So we can clearly see that, like all alkaline earth metals, if calcium gives up 2 electrons, its new outer ring has 8, which makes it very stable. Okay? So all of those guys in column 2 like to give up 2 electrons. Okay, next family, the transition elements. the transition metals. So like all metals, they want to give up electrons. This area runs from here to here, families 3 to 12, okay? Because they are metals, they give up electrons, but are not nearly as reactive as those first two families. They include the metals that we're most familiar with. These metals, these transition elements, tend to lose 1 or 2 valence electrons when reacting with other elements. Okay? Not as easy to predict, so I would not expect you to be able to predict the number of electrons for the transition metals. Okay, now, moving on. The next 4 families, you do not have to memorize a name, and I'll tell you why. You're allowed to use a periodic table on your test, and the next 4 families are named after the first element in the column. And so if you can look at your periodic table, you'll know this is boron family, carbon family, nitrogen, and oxygen. Okay, so our 13th family is the boron family. And if we look at the 3 part of the 13, that's telling us it has, that whole family of elements has 3 valence electrons. It includes boron, which is a metalloid. It's a semiconductor. Okay, but the rest of the elements in that group are metals. So they tend to want to give up electrons because that's what metals do. So these elements have 3 valence electrons, which they give up to other elements when chemically reacting. All right, again, and when they give up those 3, then that makes them stable. If you want to leave, you can do that. If you want to leave, you can do that. We're not doing that. Okay? All right. So the next one is family 14, and that is the carbon family. That's the carbon family, family 14. They all have 4 valence electrons. All right. So this family includes a nonmetal, metalloids, and metals. Carbon is an element that's found in all living things. All right. And again, that 14, if we look at that second digit, that tells us every element in that group has 4 valence electrons. We're starting to move into more and more nonmetals now as we move to the right. Okay, so these elements have 4 valence electrons that they tend to share with other elements when forming compounds. Carbon and other elements in this group tend to form 4 chemical bonds with other elements by sharing 4 electrons. Now, before you flip the page, I want to give you an example of why it works to share 4 electrons. Okay, so I'm going to, I want you to write down CH4. This is methane, which is natural gas, very common element. And I told you carbon tends to make 4 bonds with other elements. So you're going to see why this works. Again, carbon has 4 valence electrons. So we're going to draw like a little Lewis dot here, and we're going to put 1, 2, 3, 4. But remember, atoms want to have 8 in their outer ring, or they want to have a full ring. So we're going to put the hydrogen atoms. Here's a hydrogen, 2, 3, 4. I got 4 hydrogen atoms, and hydrogen is in column 1. So hydrogen has 1 valence. Now, because you can't see my red and blue colors here, I'm going to do my hydrogen valence electron with an X. So there's my hydrogen valence electron. Each of these hydrogens has 1 valence electron. So I want to show you why this compound works. When carbon shares with hydrogen and it hogs all the electrons, carbon now has 1, 2, 3, 4, 5, 6, 7, 8. The reason, Connor, atoms chemically bond with each other is to get that full valence shell, or a shell that has 8 electrons, okay? Now, hydrogen only has 1 ring, and the first ring for any element can only hold 2 electrons. So when the hydrogen hogs the carbon atom's electron, it gets its stable 2, and it is happier bonded than by itself, okay? So you can see why this compound works for both carbon and hydrogen, because atoms are always seeking to get a full valence ring or 8 in their outer ring. Okay, So now let's flip to the next page. Okay. So it just says carbon family have 4 valence electrons. And so if they share 4 with another element, the valence ring will have 8 total, making it stable. Okay, now our next family that we look at is this nitrogen family with phosphorus and so on, where they all react similarly when we're done taking notes. Okay, so the nitrogen family is family 15. It includes metals, nonmetals, and metalloids. They have 5 valence electrons. We're in family 15. How many bonds would they form? If they have 5 and they want 8, how many bonds, guys? 3. So they tend to form 3 bonds with other elements. When they bond, they mostly share electrons. So again, let me show you why a compound like this would make sense. NH3. If we were to draw nitrogen, it has 5 valence electrons. So I'm going to put 1, 2, 3, 4, 5. Now I'm going to bond it with 3 hydrogens. Hydrogen is in column 1, so it has 1 valence electron, which I'm going to draw with an X, so you can tell the difference. Okay? Again, you can see why this would make both elements stable. When nitrogen hugs the electrons, it gets 8 electrons in its valence ring, 2, 4, 6, 8. When each of the hydrogens hug them, they get 2. And the first ring, which is all hydrogen has, can only hold 2 electrons. So again, they're more stable together than they are alone. And that's why atoms bond with each other. So nitrogen is a very common element and makes up about 80% of our atmosphere. Interestingly enough, when we breathe in, we just exhale that nitrogen back out. We can't absorb it and utilize it. We have to eat food with nitrogen in it in order to get nitrogen. And nitrogen is the main component in the proteins that we assemble in our body to build muscle and to grow. So we have to have a source of nitrogen. Okay, the next family is our oxygen family. It's family 16. They all have 6 valence electrons. Again, it's this family with oxygen and sulfur and so on. They all have 6 valence electrons. So how many bonds are they going to make, guys? If they want 8 and they have 6, 2. Good. So it includes metals, nonmetals, and metalloids. Elements in this family have 6 valence electrons and tend to form 2 bonds with other elements. When they bond, they tend to share electrons. So let me show you again. If we look at H2O, we see why this compound works. So if we draw oxygen, it's got 6 valence electrons. 1, 2, 3, 4, 5, 6. Now I'm going to draw the hydrogen. The hydrogen just has 1 valence electron, and we have 2 hydrogens. So again, you can see why that compound works, because when oxygen hogs the electrons, it has 8. And when the hydrogens hog them, they have 2 in their valence ring. And remember, the first ring can only hold 2. Okay? Then lastly, so again, in summary, with these 3 families, they tend to share to get up to 8 electrons in that outer ring. Now, just like the first 1, 2, and 3 give up electrons, this one will steal an electron to go from 7 to 8. It doesn't share. So the halogen family is family 17. They are mostly nonmetals, with the exception of 1 metalloid. They are never, just like families 1 and 2, found alone in nature. Because they're so reactive, they're always found in the form of a compound. Okay? They are the most highly reactive nonmetal group. They have 7 valence electrons, so they're really eager to get 1 more. So they tend to steal 1 electron from another element in order to have the stable 8 in their valence ring. So column 1 loves to react with column 7. When those metals and nonmetals bond, they form salts. So let's look at sodium, which has got a Lewis dot like that shows that it has one valence electron. Chlorine, which is a halogen, it has 7, 2, 4, 6, 7. So what ends up happening is this sodium gives an electron away to the chlorine. They don't share. Literally, the sodium gives its electron to the chlorine. So how do they bond? Well, when sodium gives up a negative charge, it becomes positive. And when chlorine gains a negative charge, it becomes negative. And opposites attract. And when they attract, it's just like opposite poles of a magnet. They stick together, and that's what the chemical bond is. And they form the compound sodium chloride, which is salt. Okay? So atoms can bond when they share electrons, or when one gives them up and one steals them, and they get opposite charges and stick together. Both of those are forms of bonds. Okay, then our last family, and again, this should all be review, is our noble gas family. Family 18, they are unreactive, or the vocab term that I told you to memorize is inert, okay, because they have 8 electrons in their valence ring, okay? So they are not found in the form of compounds, but are often found alone because they are already stable. The only exception in this group, you guys, is helium. Helium is stable when it has 2 valence electrons because the first ring can only hold 2. Helium only has 1 ring, so it is stable and inert, unreactive when it has 2 electrons. So it is still a noble gas. Last thing that I want to do today in terms of notes, I want to make sure that you understand how to do that assignment from before break if you were struggling. And also, this is going to be the directions for how you do tomorrow's assignment. So let me do one last little example thing for you. I copied off a picture of family number 13, and I want to focus on aluminum. Take good notes, and you can use this on your assignment tomorrow or anything that you had trouble on. Braden, write this down. So the number 13 here is your number of protons, okay? This number down here is your number of protons and neutrons. Remember that it's a decimal number because the number of neutrons can vary. You can have different forms of, let's say, aluminum with different numbers of neutrons, so this is an average. These over here are the electrons per ring. You do the other one. That one doesn't sharpen good. Okay, these are the electrons per ring. So let me show you how to do the Bohr. If you got stuff wrong on this assignment, this is how you do it. So your protons would be 13, and then you would write 13p in the nucleus. Your neutrons, this is the only thing you have to figure out, and we did this at the beginning of the year. You take the bottom number, which is the protons plus the neutrons. It's this one right here. You got to round it. So remember, if the number to the right of the decimal point is 5 or above, you round up. If it's less than 5, you leave it alone. So 26.9 would be 27. If you've got your protons and neutrons, you want to subtract your protons, which is the top number, in this case 13, and that'll give you your number of neutrons, which in this case would be 14. So you would write 14 neutrons in the center. So that's the only calculation that you have to do. The rest is copying. So you put 13p, you figure out the neutrons. The electrons are given to you, 2, 8, 3. So you put 2 in the first ring. You can put them anywhere in the first ring that you want. 8 in the second ring, 2, 4, put them anywhere you want in the second ring. 6, 8, and then you put 3 in the fourth ring, or in the third ring, okay? So it's really easy to tell when you look at a Bohr diagram. I know aluminum is a metal. Metals give up electrons. If I give away these 3 electrons, this ring disappears, and I have a stable 8 in my outer ring. So the Bohr diagram really helps us see that, okay? The other way to represent this, and you'll have to do both on your poster that you're doing tomorrow, is to do a Lewis dot. This is another helpful way with a Lewis dot. All you have to do is you look at your periodic table and you look at that last number. That last number is the valence ring electrons. Okay, the number of electrons in the outer ring. And that's what you do with the Lewis dot. So you write the symbol, then you pretend, if you want to do this, you can, but you don't have to. You pretend there's a box around it, and you're allowed to put up to 2 electrons on each side of the box. So an atom's going to be stable if you have 2, 4, 6, 8. But aluminum only has 3. So you can only put 2 dots on each side, okay? I'm going to put 1 on each side. That's my Lewis dot for aluminum. It's got 3 dots, so you're showing how many electrons are in the outer ring. So it's helping you to understand, yes, it's a metal. It's going to be far easier for me to give up 3 than to gain 5. So I'm going to give up 3 electrons, and that'll make me stable. So if you had trouble and you need to redo that assignment from Friday, that might be something you want to do.